Okay, Chapter 3, Section 4, the chain rule. In order to do well in this section, we have to first review compositions of functions. So let's go on a little detour before we get to the chain rule. Say g of x is equal to the square root of x minus 2, and f of x is equal to 3 minus x cubed. When we first learned how to work with functions, we had questions that would just simply ask us to evaluate it. So for example, we might have a question that looks like this. Find g of 5. Find g of 5. Okay? And so this would automatically mean that we know that the input variable x is being replaced by a 5. So g of 5 is equal to the square root of blank minus 2, where that blank has got to be a 5. And so we can write g of 5 equals to the square root of 3. Okay, so then we learned that we can actually plug in an equation or a variable. So we can also say find f of, I don't know, say something like w. Find f of w. Okay, well, you know what? Let's change that. Let's make it find f of w plus 1. Okay, so now I got to go over here. Here are my instructions. The input is x. X gets cubed. 3 minus 3 cubed. Okay, so this is going to be equal to 3 minus blank cubed, where that blank has got to be that w plus 1. Okay, you can simplify it after that. You got to cube this. You got to distribute the minus, cancel like terms. Okay, so I'm not going to do that, but this is what it equals. Okay, so we can evaluate a function at a number. We can evaluate a function at a variable or a little equation, or we can evaluate a function at another function. So, for example, we could find f composed with f of x. Okay, and so the instructions would be wherever you see an x, replace it with an f of x. So this would be the square root of blank minus 2. And that blank is an f of x. Good. Okay, and then we can simplify this a little bit more by replacing the actual value of f. So this would be the same thing as the square root of 3 minus x squared, x cubed, minus 2. And this would be g of f of x. And now g of f of x, well, 3 minus 2 is a 1, so this is equal to 1 minus x cubed inside the root. Okay, likewise, we can do it the other way around. We could say, let's do f evaluated at g of x. And so now if we follow the instructions for the f function, wherever you see an x, we replace it with a g of x. This is equivalent to 3 minus blank to the third power, and that blank is going to be a g of x. Okay, so then we can replace the actual value of g with our stated value here. So that means that this is 3 minus blank. This is the square root of x minus 2 to the power of 3. Replacing that g value. In fact, let me put it in color. This would be the square root of x minus 2, which is that g. And so we've accomplished f evaluated at g of x. Okay, so these are both examples of composition of functions, evaluating one function at another function. Very popular in math. So much so that we gave it its own notation. So if you recall, we described this in the following way. We use f with a little circle to represent composition g. Sometimes it's just written out this way, and sometimes it has the little x. So f composed with g at x. Either one of these is referring to exactly this situation. We want to have f evaluated at g of x. Same thing, f evaluated at g of x. And as we just saw, that means that it equals to this in this situation. Okay. On the other hand, over here, it was the other way around. So the order is important. This one is saying that this one is G composed with F, or G composed with F evaluated at X. Just notation, they both mean the exact same thing. They both represent that G is going to be evaluated at f of x. G is going to be evaluated at f of x. We saw in this case that we get this. So for these two particular f and g functions, let me zoom out again. So for these two particular f and g functions, we can see that we get a different answer depending on the specific order of our composition. So here we have this, whereas over here we have this, 3 minus square root of x minus 2 to the power of 3. So the order does matter. It is possible to have some cases where f composed with g might actually give you g composed with f, so that can happen, but not always. Okay, so here is a formal description of this seen in your book. So this is the formal definition presented by your author, composition of functions. This is found back on chapter 1, probably chapter 1, section 3-ish. And it states that given two functions, f and g, the composite function, f composed with g, also called the composition of f and g, is defined by f composed with g at x, which is equal to f evaluated at g of x, right? So it's exactly what we've been working on. So similar notations are as follows. So let's say we define a new function m of x, which is equal to the composition f composed with g evaluated at x. Remember, this is a new function. This notation here is just indicating how you achieve the new function, and it's achieved by evaluating the f function at the g function. So the order matters. This has to be f evaluated at g of x, like that. And then very often we also just denote it by saying f composed with g. So they all mean the exact same thing. They're all referring to the exact same thing. What we have is we're going to have an input value come into the g function, input. Then the g function will have some sort of an out function, some output value. And then that output value will be inputted into the f function, and then the f function's output would be the final result. Okay. Let's think about the domain then. So the domain starts off definitely in the g function, right? It needs to be an x value that's in the domain of g. Then it outputs something, and that output has to be in the domain of f, and then that ultimately leads to our final results. Here's a nice little graph to depict that. Okay, so here's a great graph to describe the domain of this composition of functions. So let's take a look at these. So let's say, for example, that this left circle over here, the entire thing represents the domain of the g function. Then this entire circle here represents the domain of the range of the g function. Separately, we have this other circle here, and they overlap a little. But this whole circle represents the domain of f. And then finally, this whole circle over here represents the range of f. Let me highlight these. Okay, so let's say that this entire circle, all of it represents the domain of g, and then all of those values are transformed into values over here in the range of g. So this entire circle represents the range of g. There are values, all the possible input values to our g function come from here, and they map to something in the yellow circle. Okay, separately we have this other domain over here, the domain of f. It's a completely separate function. It's got its own set of values. So let's highlight the domain of f. So this section here is in the domain of f, but so is this. There's a little bit of an overlap. So I'm going to erase that part there and color it a different color. Okay, so we have this pink colored region here that overlaps both of these circles. So the yellow and the pink both combine to give you the range of G, but the pink and the green combine to give you the domain of f. And then finally, all of that takes you over to the range of f. So the range of f is going to be everything from here. So let's... Okay, so looking at this picture, when we want to find the domain of M, okay, the domain of M of x is all x values in the domain of the g function, such that the g of x, g of x is in the domain of the f function. Okay, so let's look at this picture. Let's say, this is how I like to think about it. Let's say, for example, that the g function represents vouchers to a domestic airline. So you only fly within the US. That's what I mean by a domestic airline. So you might have city A, city B, city C, city D. So here's a bunch of cities all inside the United States, right? This could be Los Angeles, Seattle, New York, Florida, Miami, just whatever, cities in the US. And then they travel to other cities in the US. So maybe there's some other cities over here, N and P and Q and S. So, right, so these are all cities. So we can establish connections there. So let's say that G represents a domestic airline. And on the other hand, let's say F represents an international airline, where they pick up passengers in cities within the US. So maybe they go to city W and city E and city L, right? And city Q and city, okay. So they go to these domestic places and they take you to cool, faraway places. They take you to city Theta, city Zeta, city Alpha, city Epsilon, city Beta. Exotic Greek letter cities. Okay? All right, so since we have this set up, let's pretend that we had a bunch of vouchers, free vouchers for domestic airlines, and a bunch of vouchers for international airlines. And we wanted to see what kinds of options were available for situations where you were going to first use a domestic airline to travel between U.S. cities, and then you were going to use your international vouchers to pick up a passenger from that U.S. city and transfer them over to an international flight, right? Okay, so there are two types of mistakes that can happen when you're trying to set this up, figure out all the different combinations that you can set up. You can have, or you can arrange a passenger to be picked up in a city that's in the domain of your domestic airline, meaning they pick people up from there. Okay, and then it takes them over to a city where they drop people off, right? A destination city, like city N or city P. But the problem here is that one of these cities are not in the domain of the international. They don't pick people up from there, right? So maybe you set up a flight, or you offer a flight from Los Angeles to Seattle, and that's great, but then the international vouchers you have, they don't pick people up from Seattle. So that passenger is kind of stuck there now, right? On the other hand, there could be cities where the international airline does pick people up from. Maybe they pick people up from Miami. But perhaps the vouchers you have don't take anyone to Miami, so there's no way to use that voucher there, right? So based on your vouchers and the limitations you have, you got to consider your options. And so all your options are going to be cities that start in the US that are in the domain of the domestic airline that take you to another destination within the US that are in the range of this domestic airlines, right? They pick people up and they drop people off. So you want to get all those combinations such that the place where you drop them off is a place where the international airline picks people up so that you can have a connection going. So you want to go from San Diego, that's in the domain of the domestic, and it takes you over to New York City, and New York City is in the domain of the international, and then that takes you off to some cool faraway place, right? Okay, so in this graphic then, so in this little picture, this little blue shaded region here is representative of all the values in the domain of your G, such that they map to this little pink area here, which is in the overlap, meaning that those are the values that are in the range of G, that happen to also be in the domain of F, and then those values are the ones that map to your final destination over here. Okay, so this little football-shaped blue region is all the outputs. Now, if we take away the middle magic here and you just present to someone what's the input, what's the output of the M, then this little blue region over here is the domain of M, just this little blue region, and then you kind of ignore all that magic stuff in the middle and you go, okay, well, the range of M is this little football region over here, right? Only when you dive in there that you see that there's a connection in the middle, so you have to make sure that all the values in the domain of G are in the lead to an output G of X such that the output G of X is in the domain of F, and then ultimately that leads you to your final range of M. Okay, so I hope that kind of helps kind of visualize what it takes to figure out the domain of a composition of functions. So in practice, in actuality, it can get really hard. Once you throw in some actual mathematical equations, you have to think about what is the domain, what is the range, what's the overlap. So it can get a little difficult. We rarely ask students to figure out the domain of a composition of functions, only in cases where the functions are super easy and easy to figure out, but they can very quickly get out of hand. So that's not a skill we really require. We don't really require too much of that from students. So I wouldn't worry too much about that, but it's nice to at least get a conceptual idea of what the domain should be, even if we don't really ask you to find it very often, only in very, very simple cases. Okay, so hopefully all this looks somewhat familiar from your pre-calculus class, but how is this relevant to what we're going to be doing now? Well, in this next section, we're going to really require you to think about composition of functions, but sort of in the reverse direction, where a very complicated function is presented to you, and what we want to do is be able to visualize it as the result of a composition of functions, right? So normally when you're first introduced to this, you're given the function f, you're given the function g, and you're asked to figure out what is that composition of functions, find m of x. On the other hand, in this section, you're going to be given m of x, and then you're going to be asked to visualize what the f and the g functions should be or could be, such that when you compose them, you get the m of x. Okay, let me show you an example. So we might be given a function that looks like this, the square root of 3 minus x cubed, for example. Right? That's kind of a complicated looking function, but what we can do is think of a way to separate this as a composition of two functions such that it might be a little bit easier. And there's actually more than one way to do this. The first and most easiest way to do this is to, or I should say most obvious way to do it, I think, is to think of everything inside the square root as a separate function being plugged into the square root function. So we could say, for example, if f of x is equal to the square root of x, and let's call it w, let's call it h of x is equal to the stuff inside here, 3 minus x cubed, then we could say that f g evaluated at h of x is the same thing as g evaluated at 3 minus x cubed, which is exactly that guy. That's the square root of 3 minus x cubed. So we can say that this whole thing is f of x. So f of x can be thought of as this composition, g composed with h. Okay? And in this section, we also like to introduce this language of the inside function and the outside function. So in this situation, this is what we call the inside function. Inside function. And we call this guy out here the outside function. Outside function. Okay, let's do another example. Let's say f of x is equal to square root of x plus 2 cubed plus 4 square root of x plus 2 squared plus 4. Let's make it plus 3. Yeah, so let's say this is the more complicated function, and we're like thinking about how can we simplify this. So one way to do it is to think of these guys as the function that's being plugged into the outer function. So this could be the inner function. So I can think of, for example, the outer function g of x could be equal to x cubed plus 4x squared plus 3. And the inside function h of x could be thought of as the square root of x plus 2. And so this can be thought of as f of x is really equal to g evaluated at h of x, which is g composed with h. Good. Okay, so again, we like to introduce this notation of thinking as the h1 as the inside function, inside, and this one as the outside function. Okay, the inside function, the outside function, we want to be able to rewrite it this way and visualize it like this. It'll make this section go much smoother if you can think of it that way. Okay, so how is this useful? How is this relevant to calculus? Why do we care about this? Okay, let's move on. So let f of x be a differentiable function at x, meaning f prime of x exists. Okay, so now let's find the derivative with respect to x of f of x squared. Okay, so we're going to try and establish a rule by looking at patterns, right? So we're going to do a pattern for a couple of these, and hopefully something pops out of it, and we can extrapolate that to a more general rule that we can use. Okay, so if we want to find the derivative of f of x squared, right? So the whole thing's being squared. In fact, let me put it in a different color, just so that it's clear that this whole thing is being squared. And I want to find the derivative of this whole thing squared. Okay, so, well, this is the same thing as multiplying them together, right? They're being squared. So this is the same thing as f of x times f of x. And we know from the product rule that if we want to find the derivative of a product of functions, then this is going to be equal to taking turns finding derivatives. So it's going to be d dx of f of x times f of x plus, now leave the first function alone, times the derivative of the second function. Right? That's how the product rule works. We take turns. Find the derivative of the first function, leave the second function alone, plus, now leave the first function alone, take the derivative of the second function. Okay, so now the derivative of this function, well, I don't know what it is, but we're told it exists. It's differentiable. So I can just say it's f of x, f prime of x, times f of x, plus, now this one is f of x times, and the derivative of this function, well, that's just going to be f prime of x. And well, they're both identical. The order in which these guys is written doesn't really matter. So I can say that there are two copies of the f of x function times f prime of x. Okay, so we're fairly confident that that's good, right? So this is the derivative with respect to x of the f of x function being squared. Okay, fair enough. Now let's do it again for cubed. What if f of x was being cubed? Is there a pattern that we can deduce from this? Okay, so now we want to find the derivative with respect to x of f of x, but now it's being raised to the power of 3. What's the derivative of f of x being raised to the power of 3? Okay, so one thing we're going to do is we're going to say, well, that's easy. That's just equal to the derivative with respect to x of f of x squared times f of x. So again, I'm going to, just to be really clear of which one's being squared, let's say this one's being squared. So it's squared times f of x. That gives us f of x cubed, right? So it's the derivative of this, the derivative of this. Okay, well, that's again a product rule. So we just got to take turns. It's got to be the derivative with respect to x of the first one, which we said was f of x squared, f of x squared, take the derivative of that, multiply that by f of x, plus now leave that first one alone, f of x squared, times, and now the derivative with respect to x of the second one, f of x. Right? That's the product rule. We take turns. So derivative of the first one, that's this, times the second function, plus leave the first function alone, times the derivative of the second function. So that is the derivative with respect to x of f of x cubed. Okay. All right, well, what's the derivative of this? Well, that's easy. We already found it. That was the answer we got over here. That's this. The derivative with respect to x of f of x squared was equal to this whole thing. This is the answer to this. So I'm going to put it right here. This is going to be equal to 2 times f of x times f prime of x. Let me zoom in again. Okay, so all of this is the answer to this derivative. The derivative of f of x squared is this. Let me make it nicer. Okay, so all of this is that derivative, and then times f of x plus, and now we leave this one alone, so it's going to be an f of x parentheses squared, leave that alone, times the derivative of f of x, and well, again, the derivative of f of x is just f prime of x. We don't know what it is exactly, we just know it exists. It was given to us that it exists. Okay, so let's simplify this a little bit. We have an f of x here times an f of x, so those two can combine to give me 2 times, and it's going to be f of x in parentheses squared right? It's two of these being multiplied, this one, and then there's another multiple of f prime of x, plus, and okay, well then this guy here, there's nothing there, so I'm just going to copy it down, f of x, parentheses squared, times f prime of x. Okay, well these two are identical, except for the 2, but they both have a factor of x squared, f of x squared times an f prime of x. So these two will combine to give me 3, right? There's 2 here, and then there's this sort of invisible 1 there. So there's 3 copies of, and then there's an f of x parentheses squared, parentheses squared, times an f prime of x. Good. And so this is equal to this one, d dx, parentheses, parentheses, and then this gives me f of x, close parentheses, cubed. Okay, so the derivative of f of x cubed is equal to 3 times f of x squared times f prime of x. Okay, so maybe we start to suspect the pattern. So zoom back out and take a look at both of them. Okay, remember, all we are given is that f of x is differentiable. Its derivative exists, that's f prime of x. So based just on that, if we wanted to figure out what is the derivative of f of x squared, we can use the product rule, we do some work, and this is the answer we ended up with. F of x squared equals to 2 times f of x times f prime of x. What about when we had it cubed? When it was cubed, again, we can do this clever separation, rewrite it as a product. Then we can use the product rule to expand it all out like this, and this is the answer we get. Okay, so a pattern should start to emerge. Let's do one more for good measure, and I think at that point the pattern should be incredibly obvious. Okay, so last one I'll do is let's figure out what happens when it's raised to the power of 4. Okay, so now find the derivative of f of x to the power of 4. Well, just like before, we're going to do a clever separation here. We'll say that this is equal to f of x to the power of 3 times f of x. And also you could actually do squared and squared. That would be fine as well. But we're just going to stick to this one. Okay, so then by the product rule, we'll say that this is d dx of f of x cubed, derivative of the cubed one. That looks hard, but remember we already have this answer, so it's just a matter of copying it from over there, times, and then leave the second function alone, f of x, plus, now leave the first function alone. Okay, well that'll be one of these cubes, f of x cubed times the derivative with respect to x of the f of x. Okay, so let me copy this side, d dx of, and then we have f of x, and this guy is power of 4. Okay, so this, well, we have an answer. We already figured out what this guy is. This derivative, third one, from above is equal to 3 times f of x, parentheses, squared, times f prime of x. Right, just copying it from above. In fact, let's look at it over here. It's right there. The derivative with respect to x of f of x cubed, we said was equal to this. Okay, so it's f of x squared times f prime of x, and there's a 3, a constant 3 in front. Okay, so now all we have to do is bring this this f of x down. So now there's a times another term of f of x plus, now we leave this one alone, f of x, and then that whole thing gets cubed, times, and now this will be f prime of x. Okay, so we simplify, and this is f of x squared, and then we multiply times an f of x, so these two can combine. This one and this one will combine to give me the following. So this will give me that this is 3 parentheses f of x cubed, so that's one squared, and this is times one more copy of f of x, times f prime of x, plus, and now, well, there's nothing we could do there, so that's just going to be f of x parentheses the whole thing cubed times f prime of x, and again we can combine them. We have f of x cubed times f prime of x, same thing over here, we combine them, and there's this invisible 1 there. To combine, they combine to give you 4. So this will be 4, and then f of x parentheses to the power of 3 times f prime of x. Okay, so this would be d dx of the function f of x raised to the power of 4 equals this. Okay, so we did it 3 different times. Hopefully that's going to be enough to identify the pattern. It's a pretty easy pattern. So we have this one and this one. Let me erase the highlighter part of it and box it up. So we have this derivative when we have a power of 2 there. We have this derivative when we have a power of 3. And we have this derivative. Okay, let me organize them over here to the right, one on top of each other, just in case the pattern isn't totally clear. So if we have f of x being squared, and we want the derivative with respect to x, then the answer is going to be 2 times f of x times f prime of x. Okay? If we have f of x being cubed, the power of 3, and we want the derivative with respect to x of this whole thing, then this is equal to 3 times f of x being squared times f prime of x. I'm just copying it from there now, and then copying it from here now, the derivative with respect to x of f of x being raised to the power of 4, f of x being raised to the power of 4, just copying it from there, it's going to be 4 times, parentheses, f of x being raised to the power of 3 times f prime of x. Okay, so based on these, can we see what the pattern is going to be? Can we guess what's going to happen with the next one? What will happen with d dx, the derivative with respect to x of a function that is differentiable, f of x, being raised to the power of 5. F of x raised to a power of 5. What's going to happen? All right, well, the pattern I think, is pretty clear. Notice this one, when it was squared, we bring out a 2 in front. There's a 2 there. When this is being cubed, we put a 3 there. When this is being to the 4th, we put a 4 in front. So I think it should be clear that this should start off with a 5, just guessing the pattern. Good. And then when we had f of x to the 4th, the next term was f of x cubed. When we had f of x cubed, the next term is f of x to the 2nd. So I think a pretty good guess would be that this one would have an f of x raised to the power of 4. Right? I'm just guessing now, just following the pattern. There's always one less there. And then just to finish off the pattern, it looks like it always ends up with one term of f prime of x. Right? So it's a pretty simple pattern. And in fact, let's expand it just a little bit. Let's keep going and say, well, it's not to the 5th power. Let's say it's just to the power of n. d dx, and then we have an f of x raised to some power n. Let's say n is a counting number. This is where n equals to 1 or 2 or 3 or 4 or dot, 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 like that. It's one of the counting numbers, some n value. And just following this pattern again, we see that, well, whatever number it is, that's the first one you start off with, right? When we had a power of 4, we started with a 4. When you had a power of 5, we start with a 5. Power of 3, we start with 3. So here we're going to start off with an n times, and then we're going to have an f of x, right? They always have f of x's, f of x, and it always turns out that the power here is one smaller than the power there. We start with power of 5, so this has power of 4, this has power of 4, this has power of 3. Power of 3 has power of 2. There's nothing here, but we can think of it as a power 1. So this is going to be raised to the power of n minus 1 times, and then we finish it off with f prime of x. Good? Okay, so this looks an awful lot like our power rule, where we take the exponent, put it out in front, subtract 1 from the exponent. So it is related to that, except that in those cases we were dealing with a single variable, whereas here, instead of a single variable, we're saying, no, it's an actual function, f of x, an entire function f of x. We only have to guarantee that f of x is differentiable at x. Okay, so we've developed something that we call the general power rule. And this is what it looks like. So this is the theorem presented by your author. He calls it the power rule combined with the chain rule. I haven't presented or talked about the chain rule quite yet. That's because I'm doing things in a slightly different order than what he's doing. But we're heading next to finding the chain rule. So other authors call this the general power rule. So it goes by that name as well. Either way, whether you refer to it as the general power rule, as you might hear me refer to this sometimes, or the power rule combined with the chain rule, regardless of its name, this is what it says. If n is any real number and u equals to g of x is a differentiable function, then the derivative with respect to x of u to the power of n equals to n times u to the power of n minus 1 times du dx. Okay. Alternatively, you could write it this way. d dx, the derivative with respect to x, d dx of g of x to the power of n is equal to n times g of x to the power of n minus 1 times g prime of x. Okay, so this should look a lot like our power rules. Remember, our power rule indicated this, sort of the simple power rule. Simple power rule said d dx of x to the power of n equals to n times x to the n minus 1, right? What's the difference here? Well, this is a derivative with respect to x, and here's a function of x. Whereas here, we're looking for the derivative with respect to x, but then this is not written in x, this is itself a function. So if instead of just a simple little x, you had a complicated function, g of x, then this tells us, all right, well, it fits the general form of some function raised to the power of n. So we get to do the power rule. Bring the exponent out in front, subtract 1 from the exponent, just like we do over here, except for this new part, which simply states that you have to find the derivative of the u function with respect to x. Right? So another alternative notation for this would be the derivative with respect to x of u to the nth power is equal to n times u to the n minus 1 times u prime. Right? So they all say the same thing. Either way you note it, what we have is going to be some function that is differentiable. Right? So maybe, for example, x to the third power minus 2x squared, that's differentiable. And that's going to be raised to some power. How about to the power of 7? Something to the power of 7. Or maybe 3 minus e of x raised to the power of negative 4. Right? As long as n is any real number, then we'll have some function that we know to be differentiable to the power of some number, some real number. Then we can use this, this newfound rule, right? Okay, let's do some examples. So for example, let's say f of x is equal to 1 minus 5x squared. The whole thing is squared as well. And we want to find f prime of x. Find f prime of x. Okay, well, this is one where we could do it by different methods. We could use the product rule, or we can just FOIL the whole thing out and find our answer that way. Or now we can use our newfound solution. So let's confirm everything works out for us. So let's do the first option. First thing we could do is just FOIL the whole thing out. So that becomes 1 minus 5x squared times 1 minus 5x squared, which means that f of x is equal to 1 minus, and then this is going to be minus 10 x squared plus 25x to the fourth power when we FOIL it all out. And now to find the derivative, f prime of x, well, that's just going to be equal to the derivative with respect to x of this whole thing, 1 minus 10x squared plus 25x to the fourth power. By now, this should be a really nice, easy derivative. Derivative of 1 is 0. The derivative of this middle term will be equal to negative 20x to the power of 1 plus 100x to the power of 3. There, that's our answer. And we achieved it by FOILing this whole thing out and then taking the derivative. That's a fantastic option. Option number 1, expand. Okay, but that might not always work out well. As we'll see in a second, these equations can get really complicated and might be kind of hard to expand it all out. So we got to have some options. Option 2 is going to be to use the product rule. Okay, so the product rule, we can say that f of x is written this way. F of x is written as 1 minus 5x squared times 1 minus 5x squared. So there's definitely a multiplication going on there. So we can use our product rule. F prime of x is equal to, now the product rule says to take turns. It'll be d dx of 1 minus 5x squared times 1 minus 5x squared plus, now it's 1 minus 5x squared times the derivative with respect to x of 1 minus 5x squared. Okay, so just to be clear here, this one we're saying we're going to take the derivative of the first one, leave the second one alone. Now we're going to take the derivative of the second one, leave the first one alone. So we take turns with it. It just so happens that they're both identical. Okay, so now let's find this. This is going to be f prime of x is equal to, the derivative of this is going to be 0 minus, so that'll be minus 10x. That's the derivative of this guy, 10x, times this, times 1 minus 5x squared, plus now 1 minus 5x squared times the derivative of this one. And the derivative of this one is going to be equal to, again, same thing, minus 10x minus 10x. Okay. So we can combine them. There's two copies of things that are absolutely identical. So we can simplify it by saying that this is equal to twice one of these things. So twice negative 10x times 1 minus 5x squared. And now we can distribute just to make it look identical to that one and confirm that we have the same answer. So this would become minus 10. Minus 10 times 2 makes it minus 20x. So these two times this one. And these two times that one makes it minus minus, I know it's going to be plus. And 2 times 10 is going to be equal to 20. 20 times 5 makes it 100. 100, x to the power of 3, exactly the same answer as before. So we've confirmed that the product rule gives you the exact same answer as you would get if you just expanded the whole thing and took derivatives individually. Okay, that's two great options, but we want to explore how we would get the exact same answer using our newfound formula, our newfound rule, to get the exact same thing. So let's come over here and use this new rule. So now option 3. Option number 3, and this is called the general power rule. I'm going to zoom into here. Okay, remember our f of x was equal to 1 minus 5x squared to the power of 2. So by the first option, we expanded the whole thing. By the second option, we thought of it as a product, used our product rule. Now we can just use our general power rule. And our general power rule is going to say that the derivative is equal to, thinking of this as our differentiable function, right? In fact, I'll do a little bit more writing than you normally need to do, but just to make sure that it's clear. What I'm doing is I'm going to think, let u of x be this 1 minus 5x squared. So if I do that substitution, then this can be thought of as u of x raised to the power of 2. Good. And so now the derivative is going to be equal to 2 times the u of x, the power of 1. We subtract 1 from the exponent. So this will just be u of x. And don't forget that we still have to multiply it times the derivative of that u of x function. So this is going to be f prime of x equals to 2 times the u of x, times the derivative with respect to x of u of x. So f prime of x is going to be equal to 2 times u of x times the derivative with respect to x of 1 minus 5x squared. And the derivative of 1 minus 5x squared, that's going to be f prime of x is equal to 2 times u of x times, and the derivative of this is going to be equal to negative 10x, just like before. That's the derivative of this. And the u of x, well, we said the u of x was 1 minus 5x squared. So we resubstitute that back in here, and we get that the derivative is equal to twice 1 minus 5x squared times negative 10x. So when we distribute those, we'll see that we get the exact same answer. We end up with negative 20x plus 100x cubed. 2 times negative 10 gives you the negative 20, times 1 gives you negative 20x. Negative 20 times negative 5 give you positive 100 x to the power of 3. Okay, so there you have it. 3 different ways to get the exact same answer. Okay, so there you go. 3 different ways to get the exact same answer. So what's the advantage of this one? Why would you do it this way? Well, I think you'll see in a second that we can make this a lot more complicated and get it to a point where this becomes really our only option, right? So for example, what if our very next question was, all right, well, now you found the answer to that one. How about this one? 1 minus 5x squared to the power of 4. If you were going to do it by option 1 or option 2, that could be a lot of work, right? We have to FOIL the whole thing out for option 1. That could take a long time. You know that's going to be a very long, ugly polynomial. And for this one, for the product rule, well, same thing. You'd have to rethink it as a product of 2. You'd kind of take 2 at a time. It would just be ugly, right? I guess we already know the derivative of squared, so I guess you could think of it this way. 1 minus 5x squared times 1 minus 5x squared. And then, well, we already know the derivative of one of these since it's this. But one, that relies on you already knowing this. And 2, that's still a lot of work. So you'll see that the general power rule is really the best way to go. Okay, let's do another example, and I'm just going to avoid the other ones and jump right to our general power rule. Let's say f of x equals to 3 minus 2x cubed to the power of 13. Okay, so now it seems pretty obvious you don't want to FOIL this, right? That's multiplying 3 minus 2x cubed times 3 minus 2x cubed, 13 times. You know that's going to take you forever to figure out, likely make lots of little arithmetic mistakes, and that's just not fun. You don't want to do it that way. So our general power rule is really the best way, really the only way to do this. And so what we want to do is think of this as the inside function and the outside function. I'm considering this as the inside function. I'm thinking of this as a composition of functions. Let's let g of x equal to 3 minus 2x cubed, right? And therefore, the outside function, let's let h of x equal to x to the 13th power. Now you see that, hopefully, that if we plug in this into that, we get this one. So, as a composition of functions, we can think of this as f of x equals to h evaluated at g of x. This one gets plugged into that one. Or h composed with g, right, as a composition of functions. And again, we can start thinking about this or speaking of it as the inside function and the outside function. So here's the inside function. This 3 minus 2x cubed, we're going to call that the inside function. And now the outside function is this x to the 13th power. Outside function. Okay, so it's nothing formal, it's just language. As I start doing the more complicated ones, I kind of catch myself talking about the inside function and the outside function, and you know, that way we're clear on what it is I mean. Okay, so using our general power rule, right? So this wasn't really using it, I was just pointing that out. Okay, so f of x equals to 3 minus 2x cubed to the power of 13. Okay, so we can think of this as the inside function raised to the power of 13. So just using our rule, we know that the derivative is going to be equal to 13 times f of x, which is going to be this thing, 3 minus 2x cubed, the power of 13 minus 1, times the derivative of the inside function. The derivative of 3 minus 2x to the 3. Okay? So this is going to be f prime of x equals to 13, and then 3 minus 2x to the third power raised to the 12th power times the derivative of this, which is going to be equal to this minus 6x squared. Right? Okay, so when I took this derivative, what the general power rule tells us is that we follow the same rule that we did with power functions, right? I momentarily pretended this was just one letter, u to the 13th. And the power rule tells us to bring the 13 out in front and subtract 1 from the 13th, right? And that's what we did here. This is bringing the 13 out in front, and then it's u to the power of 13 minus 1, which is 12. So this is going to be equal to 13 times u to the 12 times u prime. The derivative of that u function is this, the derivative with respect to x of u, which is what this is. This is u prime. U prime. Okay? All right, well, let me erase all those u's. This is a much nicer, slicker way of getting to our conclusion without having to do that. But, you know, at first, if this is too much, if you're still wondering what the heck just happened, okay, well then, you don't have to jump. You know, we can learn to walk before we run. So let me redo it, but maybe take a few more steps. So this isn't a different way of doing it. I'm just gonna, you know, talk more and write more, but it's the exact same thing. Raised to the 13, we can go, okay, I know, let's let this be our u. Let u of x equal to 3 minus 2x cubed. And now I can rewrite this as f of x is really equal to u of x raised to the power of 13. So now it looks just like our rule. So now it looks just like our rule in our book. And so the general power rule says that the derivative of this function is going to be equal to 13 times that u of x raised to the power of 13 minus 1, it's going to be 12, times, and now we got to take the derivative with respect to x of the u of x function. Don't forget about times the derivative of the inside function. Okay, so then this becomes f prime of x equals to 13 times the u of x raised to the power of 12 times this derivative, the derivative with respect to x of the 3 minus 2x cubed. Okay, so now we just simplify that, and we get f prime of x equals to 13, and then the u of x, we said that was 3 minus 2x cubed to the power of 12 times the derivative of this, which is equal to that minus 6x to the power of 2. Okay, so, well, you get the exact same thing. I just talked more and wrote more, but it's the exact same thing. Okay, so if you can at least visualize what the inside function is, right? We can think of this as one single letter. U is very often the case, so let's think of it as a u to the 13th power. Treat it by the power rule. Bring the coefficient out in front, subtract 1 from the exponent. Bring the exponent out in front, subtract 1. And then just remember to multiply it times the derivative of u. Okay. right, let's do a couple more examples. So let's say f of x is equal to 1 over e to the x plus 2x. The whole thing being raised to the power of 5. Well, that's ugly. Find the derivative. Find f prime of x. Okay, so the first thing I'm going to do when we face something like this one in particular, we could use the quotient rule, of course, low d high minus high d low over the denominator squared we go, where the numerator just happens to be 1, so that's going to make it a very easy derivative in the numerator. So we could attempt to do it that way, but let's rewrite it this way. Let's rewrite it as e to the x plus 2x raised to the power of negative 5. And so now I'm going to think of this as my inside function, right? So I'm thinking of something that's of the form u to the power of negative 5. So by the power rule, I know I'm going to bring that in front, subtract 1 from the exponent, copy this, times the derivative of the inside part. So f prime of x is equal to negative 5 e to the x plus 2x raised to the power of negative 5 minus 1. Remember, we go deeper into the negatives because we're going to subtract 1, times the derivative with respect to x of the inside, which is e to the x plus 2x. So f prime of x is equal to minus 5 e to the x plus 2x to the power of minus 6 times, and now the derivative of this, well, that's just going to be equal to the derivative of e to the x plus the derivative of the 2 to the x. And that should be easy. That's just going to be e to the x, and this is just going to be a 2. So f prime of x is equal to minus 5 e to the x plus 2x to the power of minus 6 times e to the x plus 2. Good. All right, so now we can just simplify that a little bit. We're done with the derivative part. We can just say that this is equal to this term and this term are in the numerator. To get rid of the negative in the exponent, we bring it underneath the fraction. So this will be minus 5 e to the x minus 10, distributing the minus 5 and the e to the x plus 2. All over, and then we have e to the x plus 2x in the denominator. So that'll be our final answer. Oops. Don't forget that all of this is raised to the power of 6. That's our final answer. Okay, so I didn't do the actual substitution, I just kind of visualized it, right? So visualizing it can be a very useful way of doing this. I thought of this as my inside function, my u. So I thought, okay, it's a giant u, a complicated u, where u happens to be this e to the x plus 2x, u to the negative 5, so I know that the power rule allows me to bring that minus 5 out in front, subtract 1 from the exponent, so this is going to be u to the power of that, times the derivative of u. That's all you have to remember. Okay, all right, hopefully that one was not bad either. All right, let's try one more. Say f of x is equal to the cube root of x squared plus the square root of x. Well, that's fun. Okay, so one thing we could do is, again, think of this ugly thing inside here as our inside function. So we can think of this as u equals to x squared plus square root of x. And then, so we could rewrite this as f of x equals to x squared plus the square root of x, and the whole thing is being raised to the power of 1/3. And so now we can use our general rule. So f prime of x is going to be equal to 1/3 x squared plus square root of x, right? I'm just copying that, raised to the power of 1/3 minus 1. So I'm letting this be my giant u. Let u equal to this ugly mess thing here. That's the inside function. Raised to the power of 1/3. So I use my general rule. Bring the 1/3 out in front. Copy this u and raise it to the power of 1/3 minus 1. That's going to be negative 2/3. But don't forget, and this is the most common mistake, don't forget, we have to then multiply it times the derivative with respect to x of the u, which in this case is x squared plus the square root of x. Good. So this is that u. Okay, so let me erase this guy and this guy. All right, so then f prime of x is equal to 1/3 x squared plus the square root of x raised to the power of negative 2/3 times, and now this is going to be the derivative with respect to x of x squared. That's going to be 2x plus, and now remember, we can think of the square root of x as x to the power of 1/2. So we'd want to do our rule there, our power rule there. So this is going to be f prime of x is equal to 1/3 x squared plus the square root of x raised to the power of minus 2/3 times 2x plus, and then this is going to be equal to 1/2 x to the 1/2 minus 1, which would be minus 1/2. So this whole thing could be brought underneath the denominator to get rid of that minus, and so can this, but it is in the numerator. Here, let me rewrite this over here. Okay, so I brought this term underneath the fraction because of that minus, and then this entire thing stays up in the numerator, but then this itself has a minus in the exponent, so it looks a little like this. So we can bring these two together by getting a common denominator. That's going to be a 2 root x. So let's multiply this by, simplify this. Let's multiply this fraction by 2 root x over 2 root x, and I'll end up with 4 times root x times x plus 1 all over 2 root x in the numerator. So this would be f prime of x is equal to 4, and then it would be root x times x plus 1, and then all of that is divided by 2 root x, and then all of that is divided by 3 times x squared plus root x raised to the power of 2/3. So one method to deal with this is to deal with the numerator, turn it into one fraction, and now we can multiply the numerator times the reciprocal of the denominator. And so we get that f prime of x is going to be this giant fraction, where in the numerator we'll find these two. This would be 4 times x times root x plus 1 times 1, that doesn't affect anything, and then the denominator will have these two. It would be 2 root x times 3 times x squared plus root x to the power of 2/3. Right? Remember, it's the numerator times the reciprocal of the denominator. That's how we get this. And now one final simplification. We can combine these two. X times root x, that's equal to x to the power of 1 times x to the power of 1/2. So this is x prime of x is going to be equal to 4x to the power of 1. Let's put it over here. This is going to be x to the power of 1 times x to the power of 1/2 gives you x to the power of 2/3. Oops, the other way around. Gives you x to the power of 3/2. Remember, we add the exponent. That's going to be 1.5. So that's what this is. X to the power of 3 divided by 2 plus 1 divided by 2 times 3 is 6. And, well, I don't really see any great benefit in trying to combine anything there. So let's just leave it alone. It'll be 6 root x times x squared plus root x to the power of 2/3. Okay, let me zoom out. Okay, so there you go. A lot of ugly algebra here, so you have to be real careful. Take a lot of time, take a lot of space, a lot of real estate on your paper to make sure you manipulate these the right way. But strictly speaking, the derivative part of this, the calculus part of it, was really done over here. Right, this is the derivative. We're done at that point. The rest, everything over here, is just ugly algebra to help you manipulate it and get it into a format that looks nicer. The primary goal is usually to make sure that you don't have any negatives in the exponent, and 2, to make it as simple as possible. You don't want fractions inside another fraction, right? That's what we have here. We have one fraction inside a larger fraction, so you want to try and simplify that and reduce it as much as possible. So a little bit of practice will let you know how to do that. Okay, let's move on. Okay, so let's take a quick look at all the ones we've done so far. In this one, we started off with a function that looked like this, and we were able to represent it this way, where we had some function, what we considered the inside function, being raised to the power of 1/3, and then we proceeded and we found our derivative. Okay, so something raised to the 1/3 was something that we could rewrite it as something raised to the power of 1/3. In the previous example, we started off with this, and we were able to rewrite it as something raised to the power of -5. Okay, and then we were able to find our answer that way. And then in the example prior to that, we started off with something raised to the power of 13. Right, so the common theme so far in everything we've done is that we were able to express our original function as some function differentiable, some function in x differentiable, raised to a particular power, right, every single time. So far, every single example we've done has been something of the form u of x raised to a power of n in some variation, where n might be a counting number, n might be a fraction, and might be a negative, but there's something in the exponent there. And then u of x is some equation, some little binomial or polynomial or some little equation here that is differentiable. So we're able to use our general power rule to solve this. The question now is, well, is there something a little bit more general? Something that doesn't limit us to just cases where we can describe it as some polynomial raised to a particular power or some inside function raised to a particular power. What if neither one of those functions is being raised to a particular function? So for example, we were able to do something like this. Square root of 1 minus x cubed, and we're like, okay, well, this can be rewritten as 1 minus x cubed raised to the power of 1/3, right? Again, with this raised to a power thing. But what if the question we want to work with is something like this? E to the power of this ugly polynomial, right? This is not as easy as that. I can't rewrite this as some equation raised to the power of n, where n is some real number, a counting number, anything like that. This one's more complicated. So we need a more powerful rule to help us deal with this, a more generic rule that will help us interpret what to do with this. Okay, I can't do the same as that. I can't just bring this out in front and subtract 1. It just doesn't make sense, right? And what's the inside function? So we have to think about what to do with this. Okay, so let's say that y is given to be m of x, which happens to be a composition of functions f composed with g in this order like that, which we know can be thought of as f composed with g of x, or just f composed with g. Okay. All those things mean the same. All right. So y is equal to f of u, where u can be thought of as this g of x. Okay, so composition of functions, we can think of it this way. So now if we want to find the derivative, let's go back to basics. Let's go back to the definition of what the derivative is. So if we want to find m prime of x, we want to find the derivative of this composition of functions, we know that this is equal to the limit as h goes to 0 of m of x plus h. In fact, let me put that in color here. X plus h minus m of x, all of that divided by h, right? Going back to basics of what that definition is for a derivative. The derivative is going to be equal to this. Okay, but the m is a composition of functions, where the input goes actually first into the g function, and then its output goes into the f function. So this is really the limit as h goes to 0 of f evaluated at g evaluated at that minus f evaluated at g evaluated at like that. And so here we have the x plus h and then an x, right? That's what it means for the m function. And the whole thing gets divided by h. Okay, so now the trick here is going to be to multiply the numerator and denominator by the perfect thing. So let's say this is the limit as h approaches to 0 of f of g minus f of g over h. Okay, so all I've done is copy exactly that from this step to that step, no change at all. And what I'm going to introduce is I'm going to multiply this by a new version of 1, right? As long as I multiply a fraction by 1, I haven't changed it at all. But the version of 1 that I want to do is this one. I want to multiply it by g of x plus h minus g of x all over g of x plus h minus g of x. And just to stay color coordinated, I better put this in blue as well, just for it to pop out. So this is x plus h, x plus h, and x. Okay, so this is a new version of 1. The numerator is identical to the denominator. I know that these would cancel out and give me a 1. And now all I want to do is flop these two, flip-flop these two, switch them around, and so I get the following. This is going to be equal to the limit as h goes to 0 of f of g of blank blank minus f of g of blank blank. And then in the denominator here, I'll get a g of blank blank minus g of blank blank. Times, and now there's still this in the numerator. This would be g of blank blank minus g of blank, and then there's still an h. Okay, so here we still have an x plus h. Here we have an x. Here we have an x plus h. And here we still have an x. Just copying this, right? So this went over here, and this went over there. So there's still an x plus an h here, and an x there. Okay, looking good. Let's keep going. Now, let's remember that this limit applies to absolutely everything. It's the limit of all of this. The limit of all of this. So it's the limit of all of this. Okay. So now let's do a little substitution. Let's let k equal to, well, actually, that's fine. Let k equal to this difference down here. It's the g of x minus h minus the g of x. X plus h minus x. Let's let that be true. And as I had written above, we're also letting u equal to g of x. U equals to g of x. So that means that k is equal to g of x plus h minus u. Right? So I'm just replacing this g of x with a u, and I can move it over, and so I could say that u plus k equals to g of x minus h. Excuse me, x plus h. Okay, all right, so now right here, I'm going to replace this guy right here. I'm going to replace it by my newfound substitution. I'm going to replace this with what do we want to replace it with? Let's replace it with a u plus k. And then this guy, well, we just said the u is the g plus h. And then in the denominator, well, this whole denominator, this whole thing was equal to k. So this whole denominator is going to be equal to k, the whole thing. Okay, so now this whole thing then can be substituted in the following way. We're saying that m prime of x is equal to the limit as h goes to 0 of, and I'll have a giant fraction here, which has f of minus f of, and so here this is going to be replaced with a u plus k, and this is a u, and then the denominator, the whole thing was replaced by k, times, and then there's this other fraction, which is g of blank minus g of blank all over an h, and this one was an x plus h, and this one's an x. Okay, so again, remember this limit applies to everything, so I should wrap it in parentheses like this. And note that based on our description of, okay, let me come back over here and fix this thing. This is m of x. This is m prime of x. This is m prime of x. Note that based on our definition of where k is, as h goes to 0, then g of x plus h will go toward g of x, which means that k will also grow to 0. Okay, so this limit as h goes to 0 can be also expressed as, or as the results in k also going to 0. And I'm going to rewrite the limit as k goes to 0 of this first one. Oh, actually, no, let's do this way. Goes to 0 of f of blank minus blank over k. And then the second one, which is g. So I'm going to say that this breaks down into this limit times, and now it'll be the limit of the second one. So it'll be the limit as h goes to 0 of g of blank minus g of blank all over h. Okay, so this first one has this u plus k, and then there's a u there over k. I should have written it in red just to make it match. Over k, and this one has an x plus h minus g of x all over h. That's m prime of x. Okay, so now this looks just like our definition of a derivative. This is the derivative of the f function at u. So m prime of x is equal to this part, which is f prime evaluated at u, times, and well, this is the derivative of the g function at x, times g prime of x. But the u was defined to be g of x, so we get that m prime of x is equal to f prime evaluated at g of x times g prime of x. All right, what does this lead us to? This leads us to a more general rule called the chain rule. Okay, so we started off with a function defined this way, y equals to m of x equals to f composed with g of x. Good. And we wanted to find the derivative. We go back to our definition of derivatives, and then we do a little bit of manipulation, and then we do this substitution here, which allows us to rewrite it this way, which is going to lead to a product of two derivatives. The derivative of f evaluated at u. Notice how this looks an awful lot like our original definition of a derivative. This is a derivative evaluated at x. Here is the derivative of m evaluated at x. Whereas here, this is the derivative of f evaluated at u. And this is the derivative of g evaluated at x. Good. So u is g of x. As defined by this, we can think of this as u being the inside function, u, which is the g of x. Okay, so here's what it looks like in a format or in a boxed up rule that your author gives you. So finally, we get to the chain rule. This is the boxed up version that your author presents to you. If g is differentiable at x and f is differentiable at g of x, then the composition function capital F, which is equal to f composed with g, defined by capital F of x equals to f composed with g, or f evaluated at g of x, is differentiable at x, and f prime is given by the product f prime of x equals to f prime evaluated at g of x times g prime of x. Okay, so this is exactly what we were just been working with. We got to think about it as the outside function, inside function, right? So the way it's presented here, the g of x is the inside function, and the f of x is the outside function. So we take the derivative of the f function evaluated at the g of x. So leave that g of x alone, treat it as a variable, as if it was just x. take its derivative, then multiply it by the derivative of that inside function g of x. Okay. An alternative notation for it is this one, dy dx equals to dy du times du dx. It's easier to remember. Maybe it looks a little elusive. So let's expand this a little bit. Remember that notation is a big deal in calculus. Lots of different ways to do things and say things, and that's part of the challenge to figure out what in the world I mean. Okay, so remember that lots of different ways to request for a derivative, and one of the ways that we very often use is to say ddx, the derivative with respect to x of some function, and that function could be the function y. And then we can take that same notation, maybe we can write it like that, but then we can also just write it as dy dx. They both mean the same thing. So this is the derivative of the y function with respect to x. This is the derivative of the y function with respect to u, and this is the derivative of the u function with respect to x, right? So we can expand that this way. ddx of y is equal to ddu of y times ddx of u. Okay, so this is assuming y is a function written in terms of the variable u. So this is some sort of little u equation in here. So we take the derivative with respect to u. And then we multiply it times the derivative of the u with respect to x, right? And it just condenses nicely the way we see it there to say that dy dx is equal to dy du times du dx. And it seems really nice. It seems pretty obvious here because you can think of canceling out the du's. This du cancels with that du. We're not going to do that right now, but there is a way to kind of think about it that way. We can think of it as like a little fraction. There's sort of a duality here where we can think of it as a little fraction, but can always think of it as a set of instructions, all right? And in order to do something to this function, define its derivative with respect to whatever variable is out here. Okay, but this makes it kind of nice to remember the pattern. So if we think of like a quick little example, let's say u is equal to x squared plus e to the x power, then we could write y is equal to x squared plus e to the x power to the third power plus about sine of x squared plus e to the x power. Okay, so this is a very, very complicated looking equation, but we can make it just a little bit simpler if we think of this as a u. So we can think of this as y equals to u to the third power plus sine of u. Now it doesn't look quite so bad, right? We can take the derivative of this. This is no problem. So finding the derivative of y with respect to u, let's do that. So now y prime is going to be equal to the derivative with respect to u of the u function, which is going to be equal to u to the third power plus sine of u times the derivative with respect to x, dx, of the u, which is this x squared plus e to the x. Good. Okay, so now this derivative is super easy. That's just going to be y prime is equal to 3u to the power of 2 plus the derivative of sine is just going to be cosine of u. And then that whole thing gets multiplied times this derivative, which is really easy. That's just going to be 2x plus e to the x. And now, as a final step, we got to come back and replace that u back again with u equals to x squared plus e to the x. Okay, so here's our final answer. The derivative with respect to x, or y prime, is going to be equal to this complicated looking thing, but we were able to break the original function into smaller pieces, smaller chunks, right? So here's the original function here. Very complicated, very ugly looking. But if we kind of envision that we can separate it as a u to the power of 3 plus sine of u, then it turns into this, right? We do a little substitution, not so bad. Then we can take the derivative of this, no problem. But then all we have to do is multiply times the derivative of u. Okay, let's do some more examples. Okay, so let's say f of x is equal to 5x to the 4th power minus 3x to the power of 7 over 2. Okay, so again, we have to think of this as a composition of functions, the inside function and the outside function. So I'm going to consider all of this to be u, one giant u to the power of 7 over 2. So u to the power of 5x to the 4th minus 3x. So I'm just going to keep that in mind. So I can think of this as u to the power of 7, u to the power of 7 over 2. If it was u to the power 7 over 2, I know I can use my power rule. And when I take the derivative would be to bring that exponent out in front as a factor, and then subtract 1 from the exponent. Right? So we just apply that rule here. This is going to be f prime of x is going to be equal to the derivative of the outside function, being this, u to the power of 7 tooths. So it's 7 divided by 2 times the u, so I copy this again, 5x to the 4th minus 3x to the power of 7 divided by 2 times the derivative of the u, the derivative of the inside part. So this becomes times the derivative of 5x to the 4th minus 3x. Good. So f prime of x is equal to 7 divided by 2, 5x to the 4th minus 3x to the power of 7 divided by 2, minus 1, right? We subtract 1 from the exponent, minus 1, times this derivative, which is going to be equal to 5 times 4x to the 3rd power minus 3. And so this simplifies as, first derivative is going to be equal to 7 over 2 times 5x to the 4th power minus 3x raised to the power of 5 divided by 2 times 20x to the 3rd power minus 3. There's our answer. So even though you might not actually do the substitution, you got to think of this as a single variable. Pretend this whole thing in here is a single variable raised to that power. Take the derivative using the power rule, or the derivative of that function, whatever that function may be. And then you just have to multiply your answer times the derivative of the thing you pretended was just a variable. Let's do another one similar to this one, using this same thing in here. See if we can see the pattern. So for example, now a completely different question. Let's say I had something similar, but let's say I had e to the power of 5x to the 4th power minus 3x. Let's add in an extra plus 5x to the 4th power minus 3x squared. Right? Okay, so you see how it would be very convenient to think of this thing as a u. So if I thought of this whole thing as just one big u, that would be e to the u. That's an easy derivative to find. And this would just be u to the 2nd power. Very easy derivative to find. So I could do the formal substitution of letting u equal to this amount. Therefore, I'd have e to the u plus u squared, and then you can find your derivative from there. Or we can just jump to the answer. But okay, so let's do the formal substitution part here. U equals to 5x to the fourth minus 3x. So that means that f of u now is equal to e to the u plus u squared. Okay, so then the derivative with respect to x, so f prime of x is now going to be equal to the derivative of our u function. It's going to be the derivative of this f of u function with respect to u. So we did our substitution. We get to take its derivative with respect to u. Good job. That's going to be nice and easy. But then we got to take the derivative with respect to x of our u function, which is this guy. Good, good, good. Okay, so then this derivative, f prime of x, then is going to be equal to e to the u, the derivative of, well, you know what, let me write it down. It's going to be d du of e to the u plus u squared times the derivative with respect to x, d dx of the u, which is 5x to the fourth power minus 3x. Good. So now the derivative with respect to u of this one is going to be e to the u plus 2u times the derivative of this one is going to be the 20x to the third minus 3, f prime of x. Okay, so now e to the u, we just come back and do our substitution. F prime of x is going to be equal to e to the x, which is equal to 5x to the fourth minus 3 plus 2 times 5x to the fourth minus 3. All of that is being multiplied by 20x to the third minus 3. Okay, so two different problems here, but hopefully we see the similarities. So let's go back over here. Let's get rid of this u and this u. Okay, so instead of doing that whole thing like that, I'll put or. It becomes very useful, very convenient to not actually do the substitution, but rather just kind of think about it and jump to our answer. So let me do the exact same thing. Let me do the exact same thing, except I'm not going to do the substitution and show you what kind of writing we could do to get the same answer. Okay, so again, even though I'm not really doing the substitution, I'm thinking of this as being a u, and this as being my u, right? They're identical. That's important for this. So it's e to the u plus u to that, okay? So when you find the derivative, pretend that's a single letter, like a u. So e to the single letter, I know its derivative is just going to be equal to e to the u. So that's going to be e to the 5x to the fourth minus 3x. Okay, so I can just say it's e to the power of 5x to the fourth minus 3x, pretending that's just a single letter. But then you got to pay the piper here. The price for pretending that this was a single letter is to multiply it times the derivative of that equation which you pretended was just a single letter. So times the derivative with respect to x of 5x to the fourth minus 3x, plus, now once again I'm going to pretend this is a single letter, u to the second power. We know the power rule tells us that that's just going to be 2 times 5x to the fourth minus 3x raised to the 2 minus 1, which is just going to be 1, times, and once again, we got to pay the price for pretending it was a single letter. So that's going to be times the derivative with respect to x of the 5x x to the 4th power minus 3x once again. Okay, so that should be easy. This is going to be e to the 5x to the 4th minus 3x times the derivative of this is going to be that 20x cubed minus 3 plus 2 times this, 2 times 5x to the 4th minus 3x times 20x to the 3rd minus 3. Okay, we can factor out this term, and then that will look exactly like that one. E to the 5x to the 4th minus 3 plus 2 times 5x to the 4th minus 3x. And then we are just going to factor out this common term. So we multiply this whole thing by 20x to the 3rd minus 3. Right, so we get the same answer. Okay, this language of the inside function, the outside function begins to creep in. And as they get more and more complicated, it becomes easier to just think about it being a variable rather than actually doing the substitution. But initially, you might want to do the substitution just to make sure that you're following along, right? We got to crawl before we run. So begin, if you've never worked with these before, begin your work with these by doing it this way. Replace the equations by a u, get to a new equation that only has u's in it, take its derivative, and don't forget to multiply it times the derivative with respect to x of the u that you substituted. Okay, so let's say y equals to this function, w plus 1 divided by 3 minus 4w to the power of 14, and we want to find the derivative. Okay, so it'll say find y prime. So y prime is going to be equal to, okay, well, let's pretend the inside is just one simple little letter. Well, in this case, I'm not using x, so I guess I could just replace it by x, right? So let's pretend for a minute that this is just x to the power of 14. That's easy. We can just use our general power rule. So this is going to be equal to 14 times the inside part. Again, we're pretending that this is just one simple letter x to the power of, and then we take the exponent and subtract 1, so it's going to be 13. Okay. Remember that there's a penalty for doing this. We got to multiply the inside, multiply times the derivative of this that we pretended was a simple little letter. So now we got to do the derivative with respect to w, ddw, of the inside part, which is w plus 1 divided by 3 minus 4w. Okay. So let's simplify this a little bit. This is y prime is equal to 14 times, now the x is that complicated thing right there, so it'll be w plus 1 divided by 3 minus 4w to the power of 13 times, and now this is a little quotient rule. Okay, so let's do the quotient rule just on this. So this whole thing gets multiplied by a very ugly fraction, which is going to be low d high, low d high minus high d low, minus high d low, derivative with respect to w of the bottom 3 minus 4w, like that, all over the denominator squared, 3 minus 4w squared. Okay, so this is a product, it's a multiplication of those two things. So low d high minus high d low over the denominator squared we go. Okay, now this is a simple derivative, no problem. Derivative with respect to w of this, that's just going to be 1. right? The derivative of 1 is 0. The derivative of w with respect to w is 1. And the derivative of this guy, that's just going to be minus 4, negative 4. The derivative of 3, that's 0. The derivative of minus 4w, that's going to be just minus 4. So let's just copy all of that and simplify. Y prime equals to 14 w plus 1, 3 minus 4w raised to the power of 13 times, and then here we have 3 minus 4w in parentheses minus, and then minus minus 4, so let's just go ahead and combine that to a plus 4 w plus 1, and then all of that gets divided by 3 minus 4w squared, and then all of that gets multiplied there. Okay, so now we can simplify by distributing this. This 4 gets distributed there, gets distributed there. There's no real reason to have these parentheses anymore. We can think of an imaginary 1 here, but it's not really needed. And we can see that when I distribute that 4, we'll end up with 4w, and here we have minus 4w, so I know those will cancel. And then I'll end up with a plus 4, and I have 3 plus 4. I know I'm just going to end up with a 7. So this whole numerator is just going to end up with 7, just in the numerator. So let's just copy that, and I think that's about as good as it gets. I guess I could multiply the 7 times the 4, but not much beyond that. Okay, so multiplying 7 times 4 gets me to 108. Is that right? 70, 98. 98. Y prime equals to 98 times w plus 1 all over 3 minus 4w to the power of 13. And since I've already pushed that 7 out in front to multiply 7 times 14, I only have a 1 in the numerator remaining. 1 over 3 minus 4w squared. Okay, now this could be a good place to stop, but also notice that if I separated these two, these fractions, I can have w plus 1 to the power of 13 in the numerator, 3 minus 4w to the power of 13 in the denominator, and then I can combine these two. Right? So I think I'm going to do that as my final step. I'll say that y prime is equal to 98 times this fraction, where the numerator is going to have w plus 1 to the power of 13, and the denominator is going to have 3 minus 4w to the power of 15. 13 from there, and then when I multiply these two, they have the same base, exponents with the same base, so I add the 13 plus the 2 to get me to this 15. I think that's about as good as it gets, and that'll be our final answer. So let me box that up and zoom out. Okay, let's do another problem. Okay, say f of x equals to this incredibly complicated function here. We have sine of x squared plus e to the x, and then that whole thing gets raised to the power of 3 times, and then separately over here we have e to the power of 3 plus sine squared x, and then that whole thing gets raised to the power of 5, and then all of that gets multiplied together. Okay, so of course the same instructions. Find the derivative, find f prime of x. Okay, so how are we going to do this? This primarily, the first thing we're going to think about is the fact that it involves a product. So we got to use the product rule. Remember, the product rule means we kind of copy it twice and take turns taking derivatives. So let me copy this whole thing. Okay, so just based on initial inspection here, this is going to require our product rule. this times this, right? So I'm going to leave this portion alone, times, and then take the derivative with respect to x of the second function, that's this one, plus, now I'm going to take the derivative of the first one, times, and then leave the second one alone. Okay, so here's our product rule. So now we're tasked with finding each of these derivatives. Okay, so now the derivative of this guy, I'm going to use my chain rule. I'm going to think of this as some function, some simple function, some single letter, some say u to the power of 5, so I know I can bring the 5, copy this to the power of 4, times the derivative of the inside part. Okay, so let me copy that down. Okay, so bring that 5 out in front, and then copy this to the power of 5 minus 1, which gives me that 4, times the derivative of the inside part. And now I got to do plus this whole thing. So now the derivative of this one, once again, I'm going to use the chain rule. I'm going to envision this, visualize this as a single happy letter. Say w, for example, w to the third power, the derivative of w to the third power with respect to w would be 3w to the second power. So that's what I'm going to do. Pretend this is one simple little letter in here. So then this will be plus 3 sine of x squared plus e to the x to the power of 2 times the derivative of the inside part, d dx, of sine x squared plus e to the x times e to the third power plus sine squared x raised to the power of 5. Okay, let me zoom out. Okay, so let's not lose track of things. Let's see here. So here's that plus sign, and then here is this plus sign. Okay, so the derivative with respect to x of this term is this whole thing right here, from here to here. I brought down the 5, copied it to the power of 4 times the derivative of the inside part, plus, and now this whole thing from here all the way out to there is the derivative of that one. Okay, plus, or times this term out here. Okay, so now all we have to do is find the derivative of this one and find the derivative of that one. Luckily, note that the derivative of e to the third power is just going to be 0. There's no variable there. That's just some number. Just like the derivative of the number 5 is 0. The derivative of any constant is 0. So that's going to be easy. And now all I have to do is figure out the derivative of sine squared x. Now over here, this derivative will also be easy. The derivative of e to the x is just e to the x. I just have to figure out what this is, the derivative of sine of x squared. So notice that these two are a little bit different. F prime of x is equal to, parentheses, sine x squared plus e to the x cubed times 5 e to the third squared x. The derivative of e to the third power with respect to x is 0. That's just some number, some constant. So it's really just the derivative of this that I care about. The derivative with respect to x of sine squared x. Okay, copy it, keep going. Plus 3 sine x squared plus e to the x squared times and now this is a little product dx of sine x squared plus, and then the derivative with respect to x of e to the x is just going to be e to the x. So I just have to figure out what that is, times e to the third power plus sine squared x, whole thing raised to the fifth power. Okay, so we're almost done. The only thing that's missing now is we have to figure out what this derivative is. I can figure out what this derivative is and what this derivative is, then we'll be set. Notice that they look very, very similar, but they're not exactly the same. So this one right here, this one is sine of x squared. So I could say sine squared x, and I want to find the derivative with respect to x of that whole thing. This one is the same thing as sine of x being squared, the whole thing, sine of x squared. And I want to find the derivative with respect to x of that whole thing. Well, this is going to be our chain function again. Let's pretend this is a simple, happy little letter raised to the power of 2. So by our product power rule, we know this is going to be 2 times sine of x, and then that whole thing raised to the power of 1, times, and then the derivative of the inside part, so then times the derivative with respect to x of sine of x. So that's going to be cosine of x. And so my final answer for this guy is going to be 2 sine of x cosine of x. Okay. Sine of x to the first power, and then the derivative with respect to x of the sine gives you cosine, so it's 2 sine x cosine x. And if we remember our identities, we know that that's equal to sine 2x. But let's leave it alone. On the other hand, this other derivative right here, let's see what that is. Let's write it down over here. That derivative, on the other hand, is the derivative with respect to x of sine of x squared. In this case, the squared applies just to the x, not to the entire sine function. These two are different. Okay, so in this case, I'm going to think of this as my happy little u equals to the x squared. So it's going to be the derivative of the outside function, which is equal to cosine. So it'll be equal to cosine of x squared times the derivative of the inside, which is going to be the derivative with respect to x of x squared. So I'll end up with cosine x squared times 2x. Okay, so you see you get very different derivatives. For this one, you get that, and for this one, you get that. Okay, so all we have to do is insert this into there and this into there, copy the whole thing, and we'll be done. That'll be the derivative. This side equals to that, and that's where this part was the derivative with respect to x of sine squared x was this one right here. And the derivative of the other one, the derivative of sine squared x, was this one. So they look very similar, but they're different. Right? Here, the squared applies to the entire sine function, whereas here, the squared only applies to the x, which is inside the argument of the sine function. So they look similar, but they're a little bit different. Okay, and then this lovely, ginormous statement is our final answer. Okay, so here's our final answer. This ginormous thing there. Can that be simplified? Maybe. There's a few things you could do to simplify this, but I wouldn't try. It is ugly as it is, so I'm happy with just finding the derivative at this point. And then, there's some stuff we can do to simplify things. There's some stuff common, some terms common to both of these. So there's a big plus sign here, and then I can combine some stuff. So this term here presents itself over here. There's 4 copies of it there. There's 5 copies of it there. So I can factor some stuff out and simplify it beyond that. But let's just leave this one alone. This is a beast. So, in your homework, I think you'll find some of the problems that are really tough. Specify. Don't try and simplify. Just find the derivative. That means you're done once you've found all the derivatives. And if you're using the chain rule several times, you gotta keep going until there's no more derivatives, and then you're done. Maybe some very simple simplifications. Very common. We like to put the 5 out in front usually, the constant. So I could have put a 5 out there, but don't do too much. Okay, let's move on. Okay, so let's say this was the function given. 7 to the power of cosine of sine of cotangent of x cubed. Okay, so note that we have several functions embedded inside each other. So x cubed is the argument of cotangent, and then all of that is inside the argument of sine, and then all of that is inside the argument of cosine. So it's not cosine times sine times cotangent. It is one function inside the other, evaluated at the other. Okay, so we get this ugly looking function, and we want to find its derivative. So find y prime. Find y prime. Okay, y prime is equal to, okay, well, we just covered this new rule. If we have b to the power of x, right, b to the power of some variable, let's say w, and we want to find the derivative with respect to w, ddw of b to the w, it's just bw times ln of b. Okay, so that's what we're going to do here. I'm going to pretend this entire exponent up here is one single letter, like a W. I'm going to pretend all of this was just W and follow my rule. So this is just going to be to copy it. Then we got to multiply it by ln of 7. And now, well, we got to pay the price for pretending this was just a single letter. We got to then multiply it times the derivative of that exponent that we were just pretending was a single letter. So next we have to figure out the derivative of d dx of that numerator, which is cosine times sine. Here, let me erase this. Okay, so now we just have to figure out what this derivative is. And again, I'm going to start off by considering all of this to be a single letter. Let me erase this ugly W from over here. So now I'm going to think of sine cotangent of x cubed as some single letter like u, and really just think about the derivative of cosine of u. So the derivative of cosine of u with respect to u would be negative sine of u. So I'm going to put this ln 7 out in front. Since it's just some number, we're used to putting the constants out in front. So I'm going to say that this is y prime equals to ln of 7 times 7 to the power of cosine of sine. So I was pretending this entire thing here was just the letter u. So cosine of u is going to be negative sine of u. So pretending all of this was just the u, let me just copy it down. Good. But now you got to pay the price for pretending it was just a single letter. Now we got to multiply it times the derivative with respect to x of the thing you just pretended was just a single letter u. So let's come over here. Times the derivative with respect to x of sine of cotangent of x cubed. Okay, so let me get rid of this. Okay, so now let's back out. That's what we have so far. So we're slowly inching along. So now we got to figure out what this is. So again, we got to take the derivative with respect to x of this whole thing. So I'm going to pretend this is a single variable. Highlight it. Now I'm going to pretend all of this is a single variable right in there. So it's sine of this. Right, it's just a single letter. Let's call it, I don't know, the letter p. Sine of p. Derivative with respect to p of sine of p would just be cosine of p. Okay, so we got to copy all of this down and then figure out what that is at the end. Okay, so that's what we have so far. Almost there. Now we just have to find the derivative of this. So once again, I pretend instead of an x squared, I have just a single letter here. So let me erase this part over here. So now I'm going to pretend all of this is just a single letter. About the letter V. It's just the letter V. So cotangent of V, find the derivative of that. So let's copy all of this down. So the derivative of cotangent is negative cosecant squared times the derivative with respect to x of the final thing, so d dx of x cubed. Last one. That one's an easy one. That's just going to be our power rule. So let's just copy this whole thing one last time. We'll be finally done. Okay, so there's our solution. Let's see, we started with y equals to 7 to the power of cosine, sine, cotangent, x cubed. So we went through several iterations of the chain rule. First, we pretended all of this was one single letter, and we know the derivative of 7 to, let's say, the letter w. We pretended all of this up here was one single letter. 7 to the letter w is to repeat it, so we just repeated it, times ln of 7. Once we're finished with that, we have to multiply times the derivative of the thing we pretended was just a single variable. Then, in order to solve this one, well then now we pretend all of that is a single variable. So the derivative of cosine is going to be negative sine of that exact same thing, we just kind of copy it down, times the derivative of the thing we just pretended was a single variable, which is times the derivative of this. Next, we pretend all of this is a single variable. right? So at this point, we've used the chain rule once here, then again there, and then again there. The derivative of cotangent, the derivative of sine is a cosine, so we just get cosine of this times the derivative of cotangent x cubed. So now we're going to pretend that this guy is just a single letter, and the derivative of cotangent is negative cosecant squared. And finally, we just have to find the derivative of x cubed to get us to our final answer. Okay, so each individual piece is not hard, but together it is one big, ugly, massive exercise here. So just make sure you take a lot of time and a lot of space on your paper. Don't try and cram it all into one little corner. Take up a lot of real estate on your paper. Be really neat and clear with your writing, particularly all those parentheses everywhere. Remember, our final answer has a bunch of multiplications. It's this term times this term times this term times this term times that term times this term, and then times ln of 7. So it's a product of a bunch of stuff. So be really clear and neat with your parentheses and take up a lot of space in order to get through this. Okay, but this should be about as bad as it gets in this section. Good. All right, so I think you have enough to be able to do your homework. So please try your homework and come to my office hours if you have any questions.